Since Sobolev functions are defined through upper gradients, there is no surprise that when the space has no rectifiable curves, we should not get any interesting class of functions for N1P. And that is exactly the case. And this does include some interesting spaces. For example, any counter set that is totally disconnected will have no non-constant rectifiable curve. And also, if you snowflake certain distance functions, you will obtain spaces without metrics. In this, for example, you can look at 0, 1, the unit interval, with the metric that is square root of the usual distance of R1. So that the distance of x and y from this line segment will be x minus y absolute value. This is what will be the Euclidean distance, as we know. And then if we raise it to power 1/2, that you can prove is a metric space again. And then you have to prove this claim that there does not exist any non-constant rectifiable path curve in this space XD. This I have actually shown in one of the videos on curves in metric spaces chapters. Okay, but let's see what the N1P space will look like here. So if a space does not have, if a space, metric measure space, does not have any non-constant rectifiable curves. Remember that for definition of upper gradient, we exclude constant rectifiable curves from definition. So if a space does not have any non-constant rectifiable curves, then N1P will be just the LP space of X with respect to the measure mu. And the proof is, well, basically just confirming the definitions. The function rho can be equal to 0, which is a Borel function, is an upper gradient to any measurable function. This is because you cannot find a counterexample why this is not an upper gradient. A counterexample would mean that you find a curve gamma so that you integrate this, and this is not bigger than or equal to a difference of the values. But the point is there are no such gammas to begin with. So it's kind of a, by default, this is a always correct inequality, and therefore that is an upper gradient. Then what was N1P space? Recall that N1P of XD mu were measurable, with respect to this mu measure, measurable functions on X with norm of the function, LP norm of the function, finite, that have some upper gradient again in LP. So 0 definitely is in LP. Therefore, under this assumption that there are no rectifiable curve, this just becomes measurable functions with finite LP norm, with norm of U, LP finite, which is none other than just LP of X. Okay, so that means the space N1P is not actually a small, but actually very large space. Every measurable LP integrable function will be in N1P. So the disadvantage, though, is that, so that's the end of the proof, the disadvantage that we cannot expect, well, N1P Newtonian Sobolev functions then will not exhibit any better behavior, exhibit any better in the sense that, well, they are more integrable, like Sobolev inequality. They are not absolutely continuous on curves. Basically, nothing can said about them that it has any hint of being smoother or differentiable or anything. So do not exhibit any better behavior than LP functions. So in the introduction to this theory of Newtonian Sobolev functions, or generally in introduction to the aims and goals of developing a Sobolev theory on metric measure spaces, was that we try to preserve some properties of classical Sobolev functions. Sobolev inequality, Poincare inequality, approximability by Lipschitz functions, trace, extension, and none of these will be holding in this context. And that is why the theory of Newtonian Sobolev functions really needs a space to have a lot of rectifiable curves. And here we went to the extreme saying that it has none at all, but also we could have a space with some rectifiable curves, but quantitatively too few, so that the end result is, again, too large of a class of functions with no fine properties compared to LP functions. Okay, so if your space has no rectifiable curves, then your N1P space is not too interesting. Fortunately, we have already talked about the Hajlas-Sobolev class of functions. And also there are other notions of Sobolev functions. On the other hand, will still be interesting. On the other hand, are not trivial. It's not all of LP in such spaces. Okay, so we've previously have had some lectures on Hajlas-Sobolev functions. We've gone through their definition and the fact that they always actually support Poincare inequality, and Lipschitz functions are dense in them. Okay, so with that, I think we can stop here and see you in some future video. Thank you for watching.